and I am a part of the Climate Change AI team and a PhD student at the University of Copenhagen's Center for Social Data Science, currently visiting at UC Berkeley's Global Policy Laboratory. For those of you who are attending the first event from Climate Change AI, we are an initiative that fosters impactful work at the intersection of climate change and machine learning by providing education and infrastructure, community building, and advancing discourse in this area. We also host a variety of different events, which you can also access online. So if you're interested in the topic of climate change and machine learning, we encourage you to check out our workshops highlighting the latest work in this area. We run these several times a year, and videos of all these past videos or events are available on the Change AI network is extensive, and you can also check out our bi-weekly happy hours where you can meet others interested in this space. The discussion forum and many other opportunities and resources available on our website and in our monthly newsletter, which also includes open calls for funding, submissions, and links to readings and courses that you might cost of carbon. And while a well-known legal scholar referred to the social cost of carbon as the most important number you've never heard of, in recent months, this has hardly been the case. The social cost of carbon has been all over the news and the subject of global, national, and domestic policy debates. But what exactly does this term mean? What is the societal cost of all the future damages associated with the change in climate due to the release of an additional ton of CO2 or greenhouse gas emissions? How has this cost been estimated in the past? And how might big data serve to inform estimates of the social cost of carbon as the full scope of climate change becomes clear? What role might AI play in this process as we move forward? Climate Change AI's webinar series seeks to highlight knowledge not just from within AI and machine learning, but also interdisciplinary perspectives from across the social and climate sciences that can provide generative dimensions for future work in this setting. And in this spirit, we are honored to have Dr. Tama Carleton, Assistant Professor of Economics at the University of California, Santa Barbara's Brin School of Environmental Science and Management, to guide us through the scientific frontier of the social cost of carbon. Dr. Carleton's research combines tools from economics with social datasets and methods from remote sensing, data science, and climate science to quantify the interplay between environmental change and economic development. Dr. Carleton is also a part of the Climate Impact Lab, an interdisciplinary team conducting a rigorous global assessment of climate change impacts. And today she'll discuss this work along with a separate recap of her recent working paper with Professor Michael Greenstone from the University of Chicago entitled Updating the United States Government's Social Cost of Carbon. Tama will have 45 minutes to present, followed by 15 minutes of Q&A at the end. So please do add your questions into the chat, and we will try our best to process them as we go. So please join me in welcoming Dr. Carleton. Thanks so much for joining us.
Hi, everyone. Thanks so much for having me. Let me just get set up. Okay, we good, Kelton?
All set.
Okay. Hi, everyone. Thanks so much. And thanks, Kelton, for that really great intro. I don't even need to give you background into the talk that we'll be seeing today, but I do just want to note, basically the idea here is how we can use empirical evidence to update a very important policy relevant number called the social cost of carbon. And a lot of the tools I'll be talking about derive from econometrics and climate science, but I'm really excited to speak to this community and get some Q&A and discussion going at the end about how we might leverage more tools from machine learning and AI to make these estimates even better and more accurate. So the overall problem that motivates the work in this area is the simple fact that lowering greenhouse gas emissions is expensive. So we all have seen many graphs that look like this, where we're looking at different possible climate futures that we may face that depend on the emissions trajectories that we choose. And we tend to sort of look longingly at this green line as a low climate risk future that we would like to have. But it's really important to acknowledge that pulling society from that red line of unmitigated emissions down to that green line is expensive. And importantly, it requires us to divert societal resources from other goals that we care a lot about, like eradicating poverty, investing in our educational systems, improving healthcare outcomes. And so policymakers are faced looking at a figure like this and trying to choose a set of policies that appropriately chooses an amount of emissions mitigation to pursue when weighing that against the costs of doing so. So just to make this a little bit more concrete, this management problem is about choosing a set of policies that maximize net benefits to society. So this has two terms, right? We've got benefits and we've got costs. And in general, the cost of a given emissions mitigation strategy has been relatively easy for us to get a number on, right? So for example, these costs might include auto manufacturers needing to retool their factories to produce electric vehicles instead of F-150s. And generally, we can get a dollar value on that relatively easily. But what about this benefits term? This represents all of the avoided climate damages from changing emissions a little bit with some policy P. So these are crops that we save from lowering the risk of drought, or people's lives that we save from lowering the risk of heat waves occurring. And these benefits occur across many different populations in the world, across hundreds of years into the future. So in general, it's a lot harder for us to get a handle on what this number is. So policymakers are left kind of struggling to weigh costs and benefits when we've got concrete numbers on the one hand and difficult way to quantify the benefits on the other hand. So this is where the social cost of carbon comes in, and it's defined as the total damages caused to society from one additional ton of CO2. And this is valued in monetary terms. So you can look at the expression at the bottom of the slide that defines this, but the basic idea is that the SCC allows us to monetize this benefits term so that policymakers are then left with an apples to apples comparison of the monetary value of an emissions policy against its cost. Now, this idea of a cost-benefit analysis for climate policy is not just sort of an abstract academic idea. This is really how a lot of climate policy is happening, particularly within the United States. And this is because many different regulations and policies legally are required to conduct a cost-benefit analysis. And since a Supreme Court ruling in 2007, greenhouse gas emissions need to be included in that cost-benefit analysis. So that leaves the government needing a social cost of carbon in order to conduct that cost-benefit analysis in line with that ruling. So in 2009, the Obama administration formed what's called an interagency working group, basically grabbing people from across government agencies to come together and figure out what the right number was for the social cost of carbon. And at the time, they turned to the best available science and economics, which was in the form of what are called integrated assessment models, which essentially integrate a model of the economy with a model of the climate to together come up with an estimate of the SCC. What you're seeing on the left here in this graph is a key component of those integrated assessment models called the damage function, which relates losses in GDP on the y-axis to total amount of warming on the x-axis. And these are the three models that sit behind the current the Obama administration SCC, which in 2020 is $52. So this number was really influential over the course of the Obama administration. It was used to value over 80 regulations worth about $1 trillion in total benefits. But then in 2017, under the Trump administration, the SCC was slashed to between $1 and $8. I'm happy to talk about the reasons why if people are interested, but this had really important impacts on actual environmental policy on the ground, because that cost benefit analysis looks very different when the benefits of emissions regulation are now much lower. So for example, the Trump administration used this lower SCC to justify rolling back fuel economy standards, which no longer pass that CBA anymore. Very recently, just last month, the Biden administration returned the SCC to that same $52, relying on the exact same framework developed under the Obama administration in 2009. So this is kind of the history of the SCC in the US at the federal level, but we also have different ways that the SCC plays out both within the US and abroad. So currently 11 different states are using the SCC and different values of the SCC to guide policy within the US. And then multiple governments across the globe also use an SCC, some of whom directly rely on the framework estimated here in the US. So these integrated assessment models are obviously really important for the social cost of carbon, and the social cost of carbon has had meaningful impact on actual environmental policy on the ground. But it's become increasingly clear that we are facing a really urgent need to update this number. You can see a quote here from the National Academy of Sciences indicating this. The basic reason is just that this is a number that is over a decade old. And as all of you in this room know, both on the climate science side and on the economic side, a lot has happened in a decade to help us better understand the impacts of climate change. And this number really should be updated to reflect that change. So luckily, the Biden administration acknowledges this. In January, a new interagency working group pulling people from across this new administration has been formed and tasked with comprehensively updating the social cost of carbon. So this is a really exciting moment for the SCC. However, it's also kind of a daunting task, right? So here you're seeing a flow diagram of all of the ingredients or the core components that lead to a social cost of carbon calculation. And this interagency working group is tasked with going into each one of these ingredients, figuring out what's happened in a decade of research, and then ultimately updating this number accordingly. And so in a recent paper that my co-author Michael Greenstone and I released, we go through each of these ingredients, sort of recap what was done originally in 2010, talk about what's happened in the research space since, and provide some recommendations on what we think should be done in order to bring this number back to the frontier of knowledge. I'm not gonna, in the interest of time, I'm not gonna go through all of these here, but what I wanna give you is an overview of some of the most important critical updates that really need to happen in order for this SCC to reflect the knowledge frontier. So the first one is that our current estimates of the damages from climate change are divorced largely from empirical evidence. So what you're seeing here are the 3 integrated assessment models that sit behind our current SCC and the empirical publications that inform the damage estimates in those 3 models. And they're plotted against the years that they're published. And so 2 things you want to take away here. First, there are not very many bars. These bars are not very high. There are not very many studies on this graph. And they're also largely outdated. These are really relatively old studies, and there aren't very many of them. In contrast, if we look at a recent literature review that we've conducted at the Climate Impact Lab, we see that there's been really an explosion of empirical evidence using large data sets, increasingly available computing power, and tools from econometrics and causal inference to carefully quantify the impacts of climate change using empirical evidence. And this graph actually stops in 2016, but we're working to update it, and you should think about it just continuing to explode. And maybe some of you in this room are working in this space. And so what this means is that all of this stuff that's happening in these blue bars are currently sitting outside our current policy landscape. So this is our first recommendation. These damage estimates need to leverage all this evidence that you see here in blue. The second one is that the climate model itself needs to be updated. So the current climate models that sit in these integrated assessment models are miscalculating the speed of warming, and they're also ignoring important feedbacks in the climate system. And one way to look at this is the graph that you see here, which shows the dynamic trajectory of a pulse of CO2 into the atmosphere. And in red, you see a median estimate from a suite of different climate models that we can consider sort of best available frontier climate science. This is the temporal trajectory from pulsing the atmosphere with a ton of CO2. In contrast, you can see that the shape and the magnitude of this impact in the 3 integrated assessment models looks very different. And depending on how you discount future damages, which we'll talk about in a moment, this can have a really meaningful impact on the ultimate SCC that we use. Our third recommendation is that we need to readdress the discount rate. So for anyone who's not familiar with the idea of a discount rate, the discount rate is the rate at which we lower the value of future costs and benefits in order to make them comparable to present values. This is a really deep, rich, complicated area that involves ethics and economics and philosophy, and I'm not going to have time to recap all of discounting here. But what I want to make clear is that we recommend in our paper that we think the discount rate needs to be reassessed, and in particular, it should be lowered if the same approach to discounting is taken as was taken in the Obama administration. So in that first working group, a sort of data-driven approach to discounting was taken in which real interest rates were relied on in order to inform the level of the discount rate. And so if we apply that same approach from the Obama administration, but update it using data, we see that real interest rates have fallen substantially, justifying a much lower discount rate. So in our paper, we argue that a discount rate should be no higher than 2%. In fact, the state of New York uses the same exact framework as our federal SCC, but applies that lower 2% discount rate and calculates an SCC of $125. So the discount rate really, really matters. And we think there's good reason, data-driven reasons to think about lowering that discount rate. And then finally, our overarching recommendation at the end, and again, I'll point people to the paper if you want to sort of get into the guts of each of the pieces of the SCC and look at our recommendations, and feel free to disagree with them. I'd be happy to talk. But our sort of overarching recommendation at the end is that if we're going to go through and update each of these individual ingredients of the SCC, we really need to assemble a new integrated assessment model from the ground up. It's going to be pretty difficult in order for us to take these ingredients and put them within the original integrated assessment models, and we argue in the paper we really should start from the ground up with the best available evidence on each of these components and build a new social cost of carbon framework. Okay, so those are sort of the policy landscape of where we are with the SCC, particularly within the United States, and where we think we can go in order to leverage dramatic changes in climate science and economics over the last 10 years. So now I want to talk about how my colleagues and I at the Climate Impact Lab are trying to contribute to this frontier of climate science and data science and economics to build estimates of the SCC using empirical evidence in a very data-driven manner. So the Climate Impact Lab is a collaboration of economists, data scientists, and climate scientists, where we are focused on bringing data to bear on this question of the SCC. And I just want to acknowledge everything from here on out in my slides is focused on work that we are doing very collaboratively. I don't know if my colleagues are here in the audience, but I want to thank and acknowledge the many people that make this type of interdisciplinary work possible. And so with this collaborative group, we are focused on the SCC and on empirical evidence to inform updates to that social cost of carbon following those recommendations I just talked through. But we're also building local level damage data. So this means going sector by sector to try to understand climate change impacts for a given location around the world for a given sector of the economy, which hopefully can help inform individuals, public sector actors, and private sector actors to prepare for climate risks ahead. So we're going to be focused on both of these outcomes. And the general overall approach that we take is to use historical evidence on both variations in our climate and variations in the outcomes that we care about to inform a projection about the future. So it's what can we learn from past data about how we've responded to the climate to learn about the future in an empirical manner. So this basically means using variation like you see in panel B from actual realized weather on the ground to build a statistical model for a relationship like you see in C, which may relate, for example, agricultural output to something like rainfall. Once we've built these statistical models, we then use climate projections to generate predictions of what the future for this social outcome may look like when we change the exposure to a different weather system and we move through a different dose response function. And I'm going to go through what this looks like for a given example, but I want to have you to have in mind the basic idea is to use our best available evidence from the past to learn about what the future may look like. So I want to show you what this actually looks like when we focus on an individual sector of the economy. Our general approach at the Climate Impact Lab is to use data from individual sectors, understand the impacts that climate change may have on that sector, and pull them together to build an estimate of the social cost of carbon. So I'm going to start with our work on mortality. The first step in this approach is to collect the best available data that we can on the outcome of interest across the globe. So here you're looking at records that we've collected for mortality from publicly available records from across the globe in as many countries as we can, varying different time periods available for varying different locations. We combine these mortality records with historical realizations of climate variables. In particular here, we're looking at temperature and precipitation to empirically estimate a statistical model relating changes in the mortality rate to changes in temperature and precipitation. And importantly, these models use a suite of non-parametric spatiotemporal controls to isolate variation in the weather that we are experiencing that is plausibly randomly assigned. So what you want to think about is living in Chicago under a slightly hotter or a slightly cooler summer and comparing that same population in Chicago to itself under slightly different climatological conditions. And when we do this, we recover what are called dose response functions, which you just saw in that sort of theoretical graph. And here, we're actually recovering a dose response function from these data from across the globe. And the most important thing to note here is that people die under extreme weather, both on the cold side and on the hot side. So we're thinking about projecting the impacts of climate change. We need to think both about cold day deaths and about hot day deaths. And importantly, that different populations respond differently. What you're seeing here is that the older population is what we're seeing is really sensitive to these increasingly hot days, whereas other populations on average are much less sensitive. Now, this is sort of an interesting dose response function for, pooling across the global sample, but what do we really care about different populations responding differently across the globe, and the fact that climate change is unfolding slowly, such that 2075 populations may look quite different than the populations we observe in our historical sample today. So to think about what this might mean, let's think about how we may use differences in sensitivity today in our historical record to learn about how future adaptation to this effect may look different. So What we do is we go to the coldest regions in our sample and we look at the effect of a hot day on the mortality rate in that region of the world and compare how that looks to different parts of the globe. What you see on the right is that in the locations that are the coldest today, we see a very strong response to a hot day, to a day at 35 degrees Celsius. These populations don't experience a hot day very often, and they're very sensitive when that population, when they do see that hot day. In contrast, as we move to places that experience these 35C days more and more frequently, we see that the marginal effect of one additional day substantially declines, such that by the time you get to the hottest regions of the globe, who experience these 35C days all the time, the effect of one additional day is much lower, reflecting the fact that these populations are better adapted to those hot days than the populations in Russia who rarely see a day that hot. So when we're thinking about generating projections of the future, we want to be able to model this type of adaptation, both in terms of their adaptation to changing climate, but also in terms of the many different socioeconomic conditions that may change into the future. So what we do is we re-estimate this statistical model I just showed you, where this sensitivity parameter, which represents how sensitive the mortality rate is to a given climatological condition on a given day, this itself is a function of conditions in a given location. And for a variety of reasons, we are using a long-run average climatological parameter, the long-run average temperature, and income per capita to determine the shape of that sensitivity reflected by beta. And so we use historical evidence on how wealthy people are and what their average climate is to learn about how those two factors change your sensitivity so that we can project across the globe and into the future how sensitive populations are likely to be as climate change gradually unfolds. And when we do this, we now have a two-dimensional model where we can see how this nonlinear function depends both on your average climate and on your average income. So to see how this works, let's go to the lower left here, where we're looking at the coldest and the poorest part of our sample. And if you look at what happens on a hot day, we see a really strong response to a hot day in this particular portion of our sample. In contrast, if we move to places that are cold on average, but also have higher incomes, we see this curve begin to fall, such that by the time you're in the richest decile of richest tercile of our distribution, we see a much more muted response on the hot day, potentially because populations can invest in adaptive technologies like air conditioning. Now, similarly, we can move to the right here as we get to hotter and hotter average climates where people expect these temperatures much more frequently. And you see that by the time you get to the richest and the hottest tercile of this distribution, we see a much more muted response to a hot day than in places that are not prepared for that effect. And this becomes really important as we think about the future, where you can see that populations are projected to move within this space as the century unfolds. And in particular, we want to think about populations generally moving up and to the right as they're projected to get richer and hotter as the century unfolds. So what we're going to do is take this model forward and model heterogeneous sensitivity to warming across the population into the future. And before we jump in and show you what that looks like, I want to just put this in context of what we were seeing in the original IAMs that sit behind the current SCC. So on the left, you're seeing DICE, and on the right, you're seeing FUND, which have very low spatial resolution relative to the heterogeneity that we know is inherent, for example, within the United States and within these large regions of the world. So what we're going to be doing is leveraging distributed computing, increases in computing availability to really, dramatically increase the scale at which we can answer this question of local level climate damages, and then use those differences in local level exposure and response to inform a social cost of carbon that reflects these differences across the globe at very high resolution. So what does that look like when we do this? First, let's just look within the locations where we estimated this response function. These are the places where we observe historical mortality rates today. What you're seeing plotted is the sensitivity to a hot day for that vulnerable older age group, where our darker red indicates a higher sensitivity of the mortality rate to a given hot day. This is within our sample. And you can already begin to see within our sample that places that are wealthier, places that are hotter have a lighter yellow color, indicating that they're less sensitive to that hot day. But the power of this two-dimensional model means that we can extrapolate this response to fill in estimates of what sensitivity might look like for the rest of the globe where we didn't have the data available in the past. And so again, this pattern really plays out here where we see poor populations, for example, in sub-Saharan Africa, being very sensitive to a hot day, as well as cold locations who are not expecting those hot days very often and don't necessarily have the technologies or the behaviors in preparation for that hot day. Now, this is what it looks like across the globe today, but what about as the century unfolds? As we just showed you, both rising incomes and gradually rising climates are likely to pull that sensitivity to a hot day down. And that's what we're seeing here as the century unfolds, and this map gets slightly lighter and lighter until by 2100, much of the world is even more adapted than some of the most adapted places today. So that map and that gradual lightening of the map showing you lower and lower sensitivity as the century unfolds reflects benefits of adaptation. We see populations lowering their sensitivity to a hot day, both through rising incomes and through their climate gradually getting warmer. But what's really important to think about here is that adaptation benefit, that lower mortality risk from a hot day, doesn't come for free. So populations have to invest in things like air conditioning or choosing not to run in the middle of the day when it's hot out, all of these variety of different costs that we have to incur in order to avoid additional heat-related death. That doesn't come for free. So when we're thinking about making these projections of climate damages, we need to account both for the benefits of that adaptation, but also the costs that people have to incur in order to achieve those benefits. So I'm not going to go into the detail here, but point you to our paper if you want to read more about it. But the idea here is to try to back out estimates of adaptation costs using observed behavior that we can see in the historical record. So this method is basically focused around the idea that people will invest in adaptive behaviors and in technologies until the costs of doing that just equal the protective benefits. So just to sort of make it a simple example, I just moved to Santa Barbara from Chicago. In Chicago, it took me like 4 days of living there in the summer to realize it was absolutely worth it to buy an air conditioner so that I could survive the summer of many days above 90 degrees Fahrenheit. In contrast, here in Santa Barbara, occasionally I will get a hot day, but it's definitely not worth it for me to invest in an air conditioner because those happen so infrequently. So what we can actually do is observe people experiencing differential sensitivity on those hot days to infer how costly it would be for them to purchase an air conditioner, for example, or incur other behavior technology changes that require them to adapt. So because we observe these benefits of adaptation, which I just showed you through the lightening of the map, we can infer estimates of what the cost of adaptation may be, and we will then include that in our projections of the damages of climate change. So what happens when we do this and we add up these damages from high resolution across the globe to give you an overall picture of what happens at global scale under warming? First, I want to give you sort of a benchmark projection that ignores some of the components that we've been talking about. So what happens if we generate a projection that ignores the fact that populations are likely to adapt as a century unfolds? We see that we project mortality rates across the globe to increase by over 200 deaths per 100,000 under a high emission scenario by the year 2100. Just to put this in context, in the US, our auto fatality rate is about 11.5 to 12 deaths per 100,000. This is a really large number. But if we allow populations to experience projected income growth benefits, this is from one of multiple different scenarios that we model, we see really large declines in the mortality effect due to the benefits of income lowering people's sensitivity to heat day deaths. Additionally, if we allow populations to respond by adapting to a gradually changing climate, this number declines even more. And when we add back in our estimates of adaptation costs, we get to a number that's about 85 deaths per 100,000 at end of century due to a high emissions warming scenario. Now, of course, these are averages across the globe and averages over a large amount of uncertainty. So we take really seriously multiple forms of uncertainty that come to play here when we're thinking about projecting a damage out 100 years into the future. So importantly, there's uncertainty in that statistical model that I showed you. There are confidence intervals in our ability to relate the impact of a hot day on mortality rates, but there's also uncertainty in what the climate might look like under a given emission scenario. So we run a set of Monte Carlo simulations to sample from both forms of uncertainty and characterize the full distribution of climate damages in a given year into the future. And so we take this approach, and I'm showing you here the global effect, but of course, this comes from local level estimates, and these impacts look very different across the globe and have differential degrees of uncertainty depending on where you are in the globe, what your dose response function is predicted to look like, and whether the climate models agree on the magnitude of warming in your location. In general, places that are currently hot today are seeing large increases in their mortality rate, due to a high emission scenario, whereas there are regions of the world, particularly that are very cold and relatively wealthy, where we actually see declines in the mortality rate because we're saving lives due to the cold day deaths that I showed you in that curve at the very beginning. And some of these places, the magnitude of the effect is very clear. So in Oslo, there's not a lot of there's not a lot of uncertainty around the fact that lives are likely to be saved. In contrast, there are regions like Delhi, where there's more uncertainty about that future. And the power of this approach is that we can characterize these effects at local level, but also being sure to characterize the uncertainty in each location. So how big are these effects? In terms of, I just showed you that there's a lot of heterogeneity, but if we want to think on average across the globe about the magnitude of these impacts, we can compare them to the current burden of disease from key leading causes of death. So if you look at the global average here on the left, you see that it's approximately equal or a little bit higher than all of the deaths currently caused by infectious disease. But this looks very different for different populations across the globe, with the highest burden being faced by the lowest income populations today. And we can see really different patterns across these different income groups based on whether they're incurring burdens from climate change via increases in death risks or via expenditures on adaptation. And what you see in the higher income locations is that there's a much lower burden of actual death rate changes. And in some cases, in the highest income places, we actually see those lives being saved. But there's a larger expenditure being due to climate change. There's much more expenditure on adaptation as opposed to increases in death risk. But overall, these effects are, in low-income countries, this is equivalent to the overall burden from cancer across the globe. So these are really large effects. So I just gave you sort of projected impacts of climate change. This sort of answers the second goal of the Climate Impact Lab, to provide local level estimates of climate risk in a sector by sector manner. But what we ultimately want is the social cost of carbon, right? And so what we do is we build an empirical version of those damage functions that I showed you at the beginning of the talk. So we take these Monte Carlo simulations, and for each one of those simulations with high resolution impacts around the globe, we index it against the total amount of warming that climate model predicts. So here you can think of each one of these points as one simulation run for a given emission scenario under a given climate model. These blue dots here represent a low emission scenario, and then these red dots indicate what happens under a high emission scenario of RCP 8.5. So with all of these simulations, we can now empirically estimate what the shape of this damage function looks like, directly calibrating that shape from this empirical model. And we see that it is, largely quadratic, such that these marginal effect of warming looks slightly higher at larger amounts of GMST. And again, there's a good amount of uncertainty in this estimated damage function. So the power of the damage function is that it allows us, just like in those integrated assessment models, to compute the marginal effect of a pulse of CO2, which gives us the calculation of the social cost of carbon. So the way this works is that we have that damage function I just showed you. And then on the climate side, we pulse the climate model with a ton of CO2, which has a dynamic trajectory on CO2 concentrations in the atmosphere and a differential dynamic trajectory on temperature change itself. This temperature change, we can convolve with that damage function I just showed you to ultimately get a damage calculation due to that pulse in every single year, which for the SCC, we then discount to get a present value of damages in each year. Again, we do this by resampling the climate model and the damage function to fully characterize uncertainty, both in terms of the shape of that damage function and in terms of what the climate system is going to do in response to a pulse of CO2. And when we combine all of that together, we get estimates of what we call a partial social cost of carbon, which represents the social cost of a ton of CO2 only via the channel of increasing heat and cold related mortality. And as you can see, there are many different ways we can think about turning these estimates of lives lost due to climate change into dollar values. And in the paper, we go into a lot of detail around the different choices that can be made around this valuation. But under a variety of different, you can see here the results under a variety of different discount rates shown on the top and valuation scenarios in panel A and panel B. Our preferred estimates sit here in these first two rows and first column, and we see that the SCC due only to the mortality impacts of climate change ranges from between about $17 to $37 in 2020. So that's sort of the entire pipeline for one sector. And I want to now walk through much more briefly what it looks like in other sectors so that we can begin to see how we can pull these pieces together to ultimately update the social cost of carbon. So the second sector that I want to talk about is energy consumption. Again, when we're thinking about measuring the impacts of climate change on energy consumption, we're going to do a data-driven approach where we're going to go to the historical record and assemble the best available data we can on energy expenditures. That for us turns out to be the International Energy Agency, which gives us empirical data on energy consumption from 146 countries. And we're going to think about dividing this data into electricity demand and other fuels demand. Again, we estimate these dose response functions using variation in the weather that these countries experienced in the past to inform the shape of the relationship between consumption and daily temperature. And so what you're seeing on the right is a U-shaped response curve, which we recover for energy expenditure for the richest decile of our population. This is a curve that if anyone's worked in this space, we see in much prior literature, which has largely been estimated in relatively wealthy locations. And electricity consumption increases both on cold days and on hot days. However, what we find is that this is much more muted in poorer locations around the globe. So we still see this U-shaped relationship, but in poorer populations, it's not nearly as extreme. But what's really important is that for the majority of the global population, people are not wealthy enough to actually see energy consumption respond to daily temperature. So a lot of our prior knowledge have been formed around curves that look like this on the right, when in fact, a good proportion of our global population doesn't experience sensitivity to temperature at all with respect to their energy consumption. And this is important both when we're thinking about differences in sensitivity of populations around the globe today, but importantly into the future, as we know that these countries are expected to move through this income space under different socioeconomic scenarios out into the future. So we want to think about building projections that allow these populations to move in this space and experience very different response functions dependent on the income that they're projected to have. Now here you're seeing the effect for electricity. The story looks pretty similar when we look at other fuels, which are largely used for heating demand. And so we see that largely other fuels demand increases on cold days without much of a response on the hot side, which makes sense. But again, this is a much stronger effect. Oh my gosh, I'm sorry. A much stronger effect in the richest portions of our population and much more muted in poorer locations. So just like with mortality, we're going to take this model and model both its responsiveness to income as well as responsiveness to the long run average climate in that two-dimensional way that I just showed you to generate projections of energy demand under climate change. First, let's look at what happens to electricity. Here again, you're looking at RCP 8.5, so a high emission scenario, end of century, and this is the total change in electricity consumption per capita by end of century. And this is sort of a familiar pattern that we saw in mortality, where today's poorest and importantly today's hottest locations are seeing large increases in their electricity consumption. In places that are relatively cold and also relatively rich, we're seeing declines in electricity consumption because of those the U-shaped nature of the curve, such that we're saving electricity on cold days. This looks in terms of interpreting these magnitudes, let's look at a couple key countries that sort of paint the picture of how big these effects are around the world. If we go to the United States, these electricity demand effects represent a tiny share of current consumption. So this overall effect in the US is only 2% of today's current electricity consumption. This looks quite different in a place like India, where partly because India's consumption per capita today is quite low, these changes in electricity demand represent a very large share of current consumption, potentially reflecting the need to really think about how the electricity and energy system is going to respond to climate change in the future. Now, this map looks slightly different when we look at other fuels. So the other fuels, again, are largely used for heating. And so we're going to see savings of these other fuels under climate change as we need to use heating much less for those cold days. And the same sort of story follows through with these magnitudes, in which in the United States, these effects are relatively small when you compare them to current consumption of other fuels, whereas in places like India, they're relatively large when we look at the size of that effect relative to current consumption. So now we're going to bundle, just like we did through that damage function I just showed you, we're going to do the same thing here, where we're going to value these consumption damages and think about empirically estimating a damage function and ultimately producing an SCC. I'm going to breeze over that sort of important multiple steps and show you what we end up with at the end. And basically where we're landing both with mortality and with energy is clear evidence that when we empirically found these SCCs, when we expend all this energy to pull the data together and try to provide data-driven estimates of these damages, we are really getting answers that look very different than the current policy landscape. So if you focus for a moment on the left part of this graph, these are estimates of the full all-sector social cost of carbon that have been used in policy. In gold, this is the Obama and Biden numbers, and in coral or brown, whatever you want to call it, these are the Trump administration numbers. And what you're seeing on the right in gray are the components of the SCC used to compute the Obama and Biden numbers, which come from individual sectors of the economy. So some of the models that form this gold bar allow us to break out the components of that social cost of carbon, and those are what you're seeing in gray. In blue, particularly for energy and mortality, these are our estimates from the Climate Impact Lab that stand in stark contrast to those individual components from the IAM. So for energy, the sign is completely different, and for mortality, this magnitude is very, very different. For agriculture, I point you to our paper. This is not a Climate Impact Lab study, but represents another attempt to bring empirical evidence to bear on this question. And there too, we see that the sign and the magnitude are very different. And so the overall story that we're beginning to paint here as we pull these estimates together is that this exercise is likely to substantially change this overall number based on very different patterns that we're seeing in these sector-specific partial social cost of carbon estimates. So where are we going forward? So I just showed you what it looks like to do this analysis for mortality and for energy consumption. Of course, there are many other impacts of climate change that need to be included in this calculation. I'm just going to give you a window into some of our active work. Here in this paper, we're looking at labor supply responses. So here we're collecting daily diaries from individuals around the world who are reporting how much they work in increments throughout the day. And we're combining, just like we did with those other, particularly with mortality, subnational records from many different countries around the world to look at how individuals respond to those hot days in terms of how much they work. As you might expect, when we conduct a very similar analysis to what you just saw, we generate projections that depend very heavily on what sector of employment you're in. So we see on the left very substantial impacts on the amount of time worked by high-risk workers. These are workers in construction, forestry, fisheries, agriculture. And on the right, you see much more muted response for low-risk workers, probably most of us on this call, who can turn the AC on or largely be out of the extreme weather when conducting our work. And so this represents the main form of adaptation that we're seeing for labor supply. And again, we will pull this together through a damage function to ultimately estimate the component of the social cost of carbon that operates through this labor supply channel. Similarly, in agricultural output, we've assembled what we think is the most comprehensive data set on subnational agricultural records that exist. So we have 6 crops that together form about 2/3 of global calories. Same idea, we want to be able to use this rich evidence on agricultural yields from the historical record, combine it with weather realizations to estimate the sensitivity of agriculture across the globe to changing climatological conditions. And we can generate impacts of potential yield effects for these 6 different crops. Here you're seeing maize, soybean, rice, cassava, and sorghum. And again, just like labor supply, we'll kind of pull those together to line up additional bars on that bar chart next to mortality and energy to begin to build out a picture of what should the overall social cost of carbon be when we go sector by sector and bring data to bear on the question of the impacts of climate change. So where are we headed at CIL? These are a list of sectors that we are actively working on and trying to complete. As you might imagine, there's lots of other diverse impacts of climate change that we are excited to think about and engage with a very large and growing literature of people working to quantify these impacts and hopefully integrate them into an ultimate SCC that really is driven from the ground up using data from the very beginning. So there, I think I'm going to wrap up. I'm really looking forward to questions, particularly about how AI and ML can fit into this pipeline. I think as you saw, there's not a large role for it currently in our work, and I have lots of ideas, and I'm excited to hear yours about where these communities might be able to communicate more directly. Thanks so much.
Thanks so much, Tama. We will hop into questions now, and I think that's a great transition to the first question that we have, which is, how might AI and ML contribute to our understanding of the social cost of carbon in the very imminent, but also the very far future?
Yeah, great question. I'm trying to think of the right slide. So I think I have thought of two key areas here, and I'm sure there are many more. So one of them is, we are largely using tools from econometrics and causal inference to isolate the causal effect of a change in weather conditions on an outcome of interest. So, for a variety of reasons, I'm sure many people on this call are familiar with, marrying some of the tools from causal inference with the tools from ML is a very active area of research, and I'm excited to see where those two things can come together. And I think one area in particular at that intersection is figuring out what things drive the determinants of sensitivity in these curves. So what I'm showing you here is that we find that income is a really strong determinant of what the shape of your sensitivity curve looks like, what your shape of your dose response curve looks like. In our work on agriculture led by Andy Hultgren, we've been incorporating more machine learning tools because the number of components that might be determining the shape of that sensitivity is really large. The literature has proposed many different things that may determine the shape of this curve. And we've been using some basic machine learning tools to try to see if we can best predict the determinants of the shape of this curve. And I think there's probably a lot more exciting work to be done there on figuring out what determines adaptation and how we can better model that using ML tools. So that's one area that we're sort of touching on in that paper, and Andy Hultgren's really leading, but also that I think there's a lot more potential in the future. But the other, I'm not going to go all the way through my slide deck, but if you think about all the way back to the beginning of my talk where we have the ingredients of the social cost of carbon, one component of that exercise is like purely predictive and forecasting based. And that is what socioeconomic scenarios and emission scenarios will look like in the future. So when we're projecting a social cost of carbon, we need to envision a world that is the baseline world on top of which you are pulsing with a pulse of CO2. And I think there's probably a lot more empirical work that can be done characterizing those socioeconomic and emission scenarios such that we can inform these baselines with better data-driven estimates of what population demographics will look like, what emissions will look like, and what incomes will look like across the globe, ideally at higher resolution than we currently have available. But I would also really look forward to other people's ideas.
Thanks. I think we have another question which actually builds on this and goes in an interesting direction. So current estimates of the social cost of carbon largely disregard the issue of equity. That is, social damages are not equally felt in an unequal society, one with demographics that vary in both their exposure and vulnerability to climate change stressors, as you showed in some of the diagrams. A small loss to a wealthy household from an extreme event might mean homelessness in a poorer one. How might the social cost of carbon better account for the distributional damages from climate change? And do you think that ML can play a role in identifying these?
Oh, super interesting question with like a lot of richness in that question. So thank you for that great question. So there are multiple different layers here. One is to simply better describe the differences in projected impacts of climate change across the globe. So this is not answering your full question. The first question is, can we make sure that we are characterizing the fact that this map has a lot of heterogeneity in it? So existing social costs of carbon estimates ignore most of the heterogeneity you're seeing on this map, much of which is correlated with existing levels of income. Or in the case of mortality, your demographic structure will also matter a lot. And so the first is, we hope at the Climate Impact Lab, we are making an important step forward on being able to even parameterize and visualize what those differences will look like. As the question asker points to, that's different than ensuring that the differential effect of the same impact is incorporated into the social cost of carbon. The fact that $100 is very different to a wealthy household than it is to a poor household, that takes this map as given and then changes the social cost of carbon, reflecting the fact that there's differential value to differential households. And so these existing SCC numbers that I just showed you do not account for that second form. So we are characterizing the inequity in the projected impacts, but not valuing it differently for different populations. But in a paper that we're actively working on, where we're pulling all these sectors together, we are ultimately producing a social cost of carbon estimate under various different assumptions about equity and discounting and many different options, a core set of which will very directly use basic economic tools to value that difference, the fact that $100 is worth a different amount to a poor household than a rich household. You can only really do that well if you characterize this uncertainty, because this characterizes heterogeneity, so you actually know how different populations are responding, are affected by climate change. So The short answer is that this is not even really feasible without high spatial resolution. And now that we have this high spatial resolution, I think it's very important to begin computing SCC estimates that directly incorporate those equity concerns. And just one additional note is that a recent executive order by the Biden administration, which was not focused on the SCC, but was focused on regulatory review, really began to open the window to potentially including those type of equity concerns in cost benefit analysis. And who knows where this will actually end up, but I think it's exciting to see very explicit statements at that level of policy discussing these concerns of equity and maybe opening the door to including equity valuation when we're computing numbers like the SCC.
Great. And this next question, I think, speaks a little bit to not just the sort of plots that were shown in your presentation largely focused on temperature. And there was a question about other climatological variables such as extreme rainfall, sea level rise, etc.
Yes, great question. So let me pull up our sector list. So in the case of mortality and energy, you're right. These papers, we include precipitation and really don't see that there's much predictive power or important magnitude of impact. So those two results that I showed you in detail are including precipitation as a control, but not directly projecting an impact of precipitation into the future. That's obviously not going to be a valid approach for many of these other sectors. So for example, in agriculture, again, Andy Hultgren is leading. There's an enormous dimension of different climatological variables that we're considering and using basic cross-validation tools to help assess which of those seem most important, and then taking those forward, conditional on what climate models are able to give us. So certain moments of the precipitation distribution, for example, are not accurately resolved enough in climate models in order to have accurate projections of them. But that intersection of the things that are best predicting in the historical record combined with what we can project in the future or what builds the agricultural projections. And as you might imagine, they have a much richer set of weather variables than we are using in the mortality and energy sectors that you saw here. Similarly for coastal, there's a pretty different modeling framework, still data driven in the way that we've been talking about here. But of course, many other components of the weather systems, in particular hurricane modeling, needs to come into play when we're thinking about those impacts. That said, I do think there's a lot on the to-do list to improve even the ones I just showed you today. We know that humidity matters a lot for mortality, even conditional on daily average temperature. And so I think we really look forward to these numbers improving and being added to as we can explore other dimensions, for example, humidity, which currently is not included in the mortality analysis.
So on the topic of kind of things that remain to be unveiled and sort of characterized more thoroughly, there was another question about what are the sort of main current limits in terms of what the social cost of carbon does not account for. For instance, how climate change might affect biodiversity and how social and ecological systems might react to climatic changes in complex ways, including carbon taxation itself.
Yeah, great question. So as you can see, sort of by the nature of this checklist, the social cost of carbon that we think can be computed either by us or by other people going sector by sector and using data from an individual sector to inform estimates of climate damages will sort of inherently be incomplete until we check a lot more of these boxes, right? And so what we have done is tried to use existing evidence on the magnitude of these impacts to try to check off the biggest boxes first. But of course, we don't know what the biggest boxes are until we conduct this analysis. So I think it is really important to acknowledge that this is an incomplete measure of the social cost of carbon as it stands today. But we are hoping to continue to build that out and to transparently characterize what is known and unknown. So in contrast, the existing integrated assessment models, some of them do attempt to incorporate things like biodiversity loss through an ad hoc adjustment to that damage function that literally is removed from data. So, that is one approach to trying to capture something that currently is unmeasured. You don't see, biodiversity on this list yet. And instead, our approach has been very clearly measure the things that you can measure and make very clear statements about what is not included, as opposed to making ad hoc assessments or judgments about what those damages should be. I totally agree with you that, whether you want to call it biodiversity or ecosystem services, or what your framework is for thinking about those impacts, there's definitely monetized value that we should be incorporating into the SCC that come from ecosystem services or biodiversity. I think that's a really exciting area to add to this list.
Great, and we have a question now about the sort of variation in the social cost of carbon in the US, how it changed during the Trump administration to a much lower value. And there was a general question about whether the social cost of carbon calculations that the US has performed, at least in the last administration, only utilized US data and damages, or are damages from other countries incorporated as well?
Yes, great question. Okay, so this big jump that you see here from 52 to a range from 1 to 8, there were 2 key changes that were made. So it's important to note that the underlying sort of scientific framework was not changed. So the interagency working group's combination of these 3 integrated assessment models was still used, and that framework still sat during the Trump administration as the framework for the SCC, but 2 key levers were pulled by the Trump administration. One is to only count damages that fall within American borders, as opposed to global damages. And the other was to change the discount rate. And you can see this range between $1 and $8. The domestic damages one is a valid, important thing for us to engage with, right? Most cost benefit analyses within the United States only count the costs and benefits to Americans, because we're talking about American policy and we're trying to assess the costs and benefits to Americans of pursuing a given policy. And so there was precedent from other CBAs to only include domestic damages. The reason that most economists argue that this inclusion only of domestic damages doesn't make sense is because carbon is a global pollutant. So Americans are hurt the same amount when we emit a ton of carbon in New York as we do when we emit a ton of carbon in Beijing. And so we end up in a situation where we need to incorporate the likely benefits we can receive from emissions reductions in other countries in addition to our own. And so this is what economists call a classic prisoner's dilemma. And the idea is that if every country only counts domestic damages, we will lose out from all those potential emissions reductions that we could realize through other countries counting the global damages. And so, this was a very effective way to cut the SCC down to a low number, and I don't think it's really supported by economists or climate scientists. Another sort of interesting way to put this quantitatively is that our colleagues at the Rhodium Group recently calculated that in the Paris Agreement negotiation process, for every ton of CO2 that the US committed to reducing, we in return received about 6 to 7 tons of commitment from other countries. And so this type of reaction function of us making commitments and other countries also making commitments means that we actually can realize the benefits of those emissions mitigations, which is why when you have this shared global pollutant, it really doesn't make sense to only count the damages within the United States. So that's sort of the story of that. It's actually important to note that that decision was also challenged in court and taken down on the grounds of being arbitrary and capricious and not supported by scientific evidence, that choice to go down to the domestic number. I forget the second half of the question. I think that was the first half.
No, I think you actually covered both parts. And in the interest of time, we have about 3 minutes left here. I want to make sure we get to some of the other questions that have been asked. There's a specific question here about what kind of data sets or machine learning innovations may help us to better assess climate risk and account for probable damages globally. So if you had a wish list of data that would help to answer some of these questions about the unaccounted for costs of carbon, what might they be?
Yeah, so I think my overarching answer is to show you a map like this. Our maps from a lot of the sectors had a similar pattern where particularly poor and hot places are they're places that are difficult to collect data, and therefore we are attempting to build statistical models that can infer what climate change may look like in these populations, but we have to do careful analysis to try to see how good we think that guess might be, but we don't have essentially ground truth data in many regions of the world. And so I'm not exactly sure. Potentially remote sensing is an area where AI and ML together can help us fill in this map. But I do think it's really important that we think about filling in this map so that we make sure we are accurately capturing these effects around the globe. We are doing the best that we can right now, but there are giant gaping holes that should, worry all of us when we look at this map, and I think are really important going forward.
Great. And so I think we're down to maybe our last question here, which is, I think, a really interesting one related to the tipping points. So, when we look at these future projections and climate scenarios, one of the issues that sort of is more difficult to quantify or predict are potential geophysical tipping points in the sort of Earth system, but also social tipping points. And we've discussed a few of them here. How might the social cost of carbon take account some of this uncertainty and what these tipping points might be and their implications?
Yeah, this is a really good question. And it's a very active area of work, both on, just like you said, on both the climate side and on the socioeconomic side. Part of my answer is that some of the aspects of a extreme climatological world are captured in the set of climate models that we at least are using in our projections. I don't know if you remember my damage function. That damage function got out to about 9 or 10 degrees warming above year 2000. That is a very fundamentally different world than we are looking at today. So to the extent that some of the GCMs are capturing some components of that extreme climate scenario, we are attempting to model that the best that we can using evidence from the past, which we can have long arguments about whether that's the right approach, but there are some component of that I think could fall within the language of tipping point that is accounted for. There's huge other components that are not included in the GCMs, dynamics that are not included in the GCMs, and that we don't have an empirical handle on because we don't have historical precedent for them. And so I think this is an area where we should be thinking really creatively about how we can combine empirical evidence from history with other forms of modeling that may more directly try to address the problem of what happens like fundamentally out of sample when we've never seen the ocean circulation shut down. So in modern history. And so I think, this has been a very data-driven exercise. And I think that may be an area where it would be interesting and important to think about combining historical evidence with other forms of modeling, because we don't have a historical precedent for some of those events.
Well, thank you so much, Dr. Carleton, for your time. This has been super inspiring, and I'm sure I'm not the only one in saying that and feeling that way. We have a lot of comments in the chat coming in to sort of attest to that, but we really appreciate your insight here. And I also think you've done a terrific job of sort of laying out what the sort of terra incognita is, or the unknown parts of the map that future researchers in the space from AI, ML, and interdisciplinary researchers across the social sciences might work together to try to tackle. So thanks so much for sort of spearheading this. And we look forward to keeping tabs on your future work. And I also want to remind everyone to check out the sort of upcoming webinars on the CCAI website. So you can go to Climate Change AI and see what's coming up. So please check it out, and thanks so much for your time. Thanks again, Tama.
Thank you all. Thanks for being here.